Hello, today I'm going to present my master's research which investigated land cover change in a fragmented landscape in the semi-deciduous forest of coastal Ecuador and its implications for tree diversity and above-ground biomass. Substantial research has reported the consequences of land cover change in deforestation frontiers. In this picture, deforestation in the Brazilian Amazon shows a clear trade-off between conservation and resource exploitation. Here, the consequences as well as the projections tell us that unless we do something to stop this trend, much biodiversity and associated above-ground biomass will be lost. The importance of biodiversity ranges from aesthetics to ecosystem services. While carbon stored in biomass has gained recently importance because of concerns about climate change. But what about highly fragmented landscapes? In this picture, the landscape I studied in coastal Ecuador shows a different pattern. Some studies state that remaining forest patches in landscape like this are not threatened because forest remains in just unsuitable places. Land cover transitions are less clear. There are areas of regrowth, forest patches, pastures, etc. A variety of land uses. And understanding land cover change dynamics in already fragmented landscapes is critical. Areas like the biodiversity hotspots, here in red, are fragmented, so this topic has important relevance for biodiversity conservation at global scales. I wanted to contribute to fill this gap by investigating the spatial and temporal patterns of tree diversity and carbon stocks, and I used a hotspot in coastal Ecuador to conduct my research. My hypothesis was that despite fragmentation, land use transitions are possible, indicating that conservation efforts are necessary in these areas, and that land use transitions likely have a negative consequence for biodiversity and biomass. Here is a map of Ecuador, showing my study area, the semi-deciduous tropical forests. My research had two components, a field component where I inventoried trees using 60 by 60 meter plots for trees greater than 20 centimeters diameter or DBH, with a nested plot of 20 by 20 for trees between 10 and 20 DBH. I conducted these inventories in all major land cover types in the area, which included forests, secondary forests, pastures, which have some shade trees in them, and three types of forestry plantations. Here, in order in the bottom, teak, an introduced species, pachaco, a native legume, and balsa, a fast-growing species. To correct for the number of individuals sampled, are used rarefaction curves. The above-ground biomass of each tree was estimated using allometric equations and published values for wood density. To quantify land cover change over time, I processed satellite images to create a change trajectory map for 2009. First, I performed a supervised classification of Landsat images of 1990, 2000, and 2009. It was not possible to differentiate forest, secondary forest, and plantations, but I got very good separability for a land cover type that included all forested areas, pastures, bare soil, which corresponded mainly to overgrazed pastures, water, urban areas, and clouds. However, for the trajectory analysis, I knew that secondary forest and forestry plantations in the area were less than 20 years old. A trajectory analysis determines changes in land cover between two or more time periods. I concentrated my analysis to 8 transitions important for tree diversity and above ground biomass. Forest, for areas identified as forest in all 3 dates. Forest loss, for areas classified as forest in 1990 that transitioned to pastures in 2000 or 2009. Secondary forest, for 1990 pastures that transitioned to forest in 2000 or 2009. secondary forest losses for 1990 pastures that transitioned to forest in 2000 and went back to pasture in 2009. Areas identified as pastures and bare soil in all 3 days were classified as pastures. Urban and water were also based on agreement in the 3 time periods. Transitions involving the land cover type cloud were assigned to the most likely trajectory, but some remain unclassified. Here are my results. An important number of species were either endemic or listed by IUCN. The rarefaction analysis indicates that forest is significantly richer in species. Here, the dotted lines indicate confidence intervals for each curve. Pasture is not here because of limited shade trees, but species richness indicate they have more species than plantations, but less than forest or secondary forest. Forest was also the highest in biomass, followed by plantations and pasture. Something important here is that secondary forests and teak plantations have the same mean, which allow me to easily extrapolate these values to the landscape. Remember that I was unable to differentiate plantations from secondary forests in the trajectory analysis, and that teak is the dominant among the plantations. Here is the final land cover trajectory map for 2009. The red, orange, and light green colors indicate areas that experience change in land cover type. The remaining colors indicate forests, pastures, urban areas, and water. So, what are the consequences of these changes for tree diversity and above ground biomass? Here I have each transition relevant for tree diversity and above ground biomass and the number of hectares for the study area. This is the total above ground biomass. Remember that secondary forests and teak plantations had the same biomass mean, so the value for secondary forest resulted from that mean and it's likely to reflect closely reality. Areas of forest and secondary forest lost are areas that transition to pasture, so the red arrows indicate biomass losses from the landscape. In contrast, secondary forest, regardless of whether they are true secondary forests or plantations, indicate gains of biomass. The net biomass lost is the value at the bottom. For tree diversity, my data tells that 11% of the remaining forest in 1990 were lost, and because forest is the richest land cover type, we know there is a negative impact for diversity. Secondary forests contribute to tree diversity, but do not compensate forest losses. Here are the main conclusions of my work. Despite fragmentation, approximately 34% of the landscape experienced change in land cover, indicating dynamism. The consequences for diversity as expected were negative, but the consequences for above-ground biomass were minimal. I also found synergies between diversity and above-ground biomass, which indicates the potential of carbon storage for promoting conservation. Finally, I think it is important to mention that many species were endemic or listed by IUCN, highlighting the conservation value of the region. My work has implications for conservation, both locally and globally. It highlights the importance of coupling biodiversity with carbon-based conservation approaches, such as REDD+ globally and the Sociobosque program specifically in Ecuador. And it also calls for similar initiatives to promote secondary forest conservation in fragmented landscapes. I would like to finish by thanking the people at institutions that made this study possible: the University of Florida and the Universidad Católica in Ecuador, the Ceiba Foundation, the Herbaria in Ecuador, and my funding sources. Thank you.